Sure. Thank you, Paul. And I'm really excited to see everyone here today, and I'm happy to visit James Cook University. And thank you again for the kind arrangements for the seminar. And today, I think I have already got enough introduction from Paul. And just another supplement is currently I'm a final year PhD student. So if there is any discussions you are interested in my research, I'm really happy to continue the discussion after the seminar. So yeah, let's start. As mentioned, there will be like 3 parts of today's seminar, and one part will be focusing on the life cycle analysis and techno-economic analysis in Southeast Asia. A second part will be focusing on Australia, is where we are locating now. And the third part will be introducing some societal research, including some interviews. So let's start here. Just for you to have an idea, I want to understand, like, people sitting here, have you heard of carbon markets previously? Yeah, I guess. So everyone has some basic knowledge for the carbon markets. And the graph showing on the right side will be the current distribution of the voluntary and compliance markets located globally. And you can see currently we can achieve 1/3 of the GG emissions among all these kind of carbon markets. But I'm not sure like how much of the emissions are actually true being removed. So let's see. But anyways, there are a useful technique, and we hopefully be an effective technique to using the carbon credits to offset these carbon emissions. And more, like nowadays, people are focusing on more durable carbon removal solutions. And one of that is like the credits trading in the carbon markets that will be involving the efforts from different stakeholders. For example, like I will introduce a little bit about the lifespan of the carbon credit. So how to issue a carbon credit? You will firstly use a technology to remove the carbon, capture the CO2 from the atmosphere and store or lock it somewhere. And then you need to introduce a monitoring and verification reporting methodology to report to the relative registries. We call it carbon registry, to officially and like legally issue your carbon credits. And these credits in the end can be traded on the market. So every step is necessary. And here we have, as we mentioned before, the durable carbon removal technologies available. But the main problem here, as the reports reported and researchers studied, the technology is still under development. So which means they need more research to understand both technically, economically, and socially, like how to deploy, how to scale up these different durable and promising carbon removal technologies and to deploy them in the right way. So here is I did some case examples of these popular technologies. For example, you can see like direct air capture. The most shortcoming people are mentioning is because you need to deploy a new technique and device in the land, which will occupy more land available in the region. And also it's introducing a new device, which will cost more upfront money cost and also some energy cost in the meantime as well. And the bioenergy, which is kind of promising, but some people are questioning about its additionality, which means if you want to issue a carbon credit, that needs to be an additional movement. If the local community are already doing this kind of movement, then this carbon credit, we will call it greenwashing because it is not additional movement to do. And in the end, our focus topic on the enhanced rock weathering, we will consider it for now as a scalable and additional movement, and also it could be like technically verified through the monitoring in our farmlands. And also from the second year, they will have a falling cost from the first year's upfront cost. And we also have some conventional solutions like planting trees in the simple words. So they are called afforestation or reforestation projects, which means you're planting trees for 20 years or even 100 years and keep monitoring on that and how much carbon is being sequestered to the trees, then that's how much carbon credit you can claim. And as we all know, there are some questions around whether the carbon capture and storage are temporary or long-term or less durable carbon removal technologies. So today, our focus will be mainly on enhanced rock weathering. Like, it sounds like a promising technology, and our answers, hopefully to answer today, is to see whether it's actually promising or not. So just introduce a little bit for any of you who haven't heard of this. The ERW, actually called enhanced rock weathering, is what we do to accelerate the natural silicate rock weathering. We will gain the rock powders, the feedstock from the mine wastes, from the basalt quarries or the construction waste, and crush them into the smaller particle size and spread them on the farmland. In this period, we will reuse the wastes from the quarry side and construction industry, so which means expanding their life cycle as a product. And what's happening in the soil is we call previously the natural weathering, but this natural weathering will need 100,000 years, longer than our human lifetime to be weathered and to capture the atmospheric carbon. But now, when we're crushing the rock powders into smaller particle size, we increased the surface area for the chemical reaction, so which can narrow down, shorten the time to less than 100 years or even 10 years, depending on different technologies and we've been studying on. So currently, we have also some previous studies showing that applying on these different crops that can increase the crop yield and plant growth. So that would be the biggest co-benefit for nowadays. And another co-benefit is when you're spreading the rock powders onto the soil, it will flow through the farmland to the river runoff surrounding and into the ocean in the end. That's hopefully where we hope it could be ended, and why we call it a durable carbon storage solution. Because in the ocean, it will be stored as a bicarbonate form, and it will store for long term. And one of the another co-benefit will be mitigate the ocean pH. So we will start our first part of the project today is analysis in Southeast Asia. So this is current research for the life cycle analysis for enhanced rock weathering. For someone who is new to life cycle analysis, this is mainly a methodology and a framework to analyze the technology deployment. So in the real world, when you're starting to do, like I mentioned before, getting the rocks from the quarry, transport them to the farmland, and then monitoring and everything coming afterwards, to counting all the emissions inside together and to calculate it out of a life cycle emission result. So this is this kind of life cycle analysis means. And the aim for that is to, instead of only doing part of the calculation for the geochemical modeling part to calculate the weathering rate and carbon capture rate, but also considering the realistic emissions happen along the way when it really happens. So currently, the academic research, you can see the red words already. The main gap will be they didn't cover the MRV part very well. So all of the research are stopping at the cradle-to-farm gate. That means they ended when we spread the rock powders onto the farmland. And they are not accounting for the MRV part, including the monitoring and sampling costs, because when you do samples, I'm sure if you are working on some field trials, you will understand that will also costing some fuels caused by the transportation between the sampling point to the lab. And when you run the lab devices, there will be electricity cost as well. So that's what it means by MRV consideration. And another consideration is that some of those haven't really considered about the environmental impacts, what we call the co-benefits, which will be brought to the agronomic industry, like the increasement of the crop yield. And all of the LCA didn't really consider that part as well. So my research to fill in these two gaps, I established this methodology to mainly understand the question, like, will it be still a positive climate solution if considering the whole life cycle of this ERW carbon credit generation and deployment? And I'm using the different models regarding the LCA and the LCIA, which is life cycle impact analysis. And including all of those, I will go through the details in the following part of the model. So this is the model itself. You can see in the middle part of the map, I will call it map, and the upper point, the green part, will be the life cycle analysis. So that's starting from the feedstock collection until the grinding of the rock powder and transporting the rock powder to the farmland and spreading it using the vectors or using the farming vehicles on the farmland, and including the MRV for the following 5 years. So this is my model for this part of the research. And the down panel will be the techno-economic analysis that will be accounting for every cost included for the transportation for each step. For example, the transportation cost or the labor cost, the technician cost, like for the lab testing. And for the upside, you can see there is an input data for the carbon removal that is based on the model called cosine. And this model are including all of the soil organic carbon, inorganic carbon, and microbial activities, and so on, into the model itself. And all the result from the model will be a carbon removal rate, like how much carbon can be absorbed and removed from per ton of rock application per hectare. So that will be the result, like that will be my input for this LCA model. And this geochemical model is introduced by my American collaborator. So if you are interested in the geochemical model itself, I can introduce you to him, and then he might be better to answer your questions. And looking back to the LCA model itself, in the left side, there is a gray-black area it's naming out the traditional aggregate industry. And this is for the scenario without enhanced rock weathering deployment. So my idea is to also consider what will happen if we don't deploy enhanced rock weathering. So what will happen will be we will still need to establish the tailing dam to store these mine tailings for the construction and also for the mining industry. And if the enhanced rock weathering happens, we will use all the wastes. So tailing dams construction will be reduced from the deployment of the technology. And on the right-hand side, it's similar. It's another supply chain for the agriculture industry. So we were considering without ERW, then the agriculture industry will need to produce more NPK chemical fertilizers. And based on that, that means that will be more emissions happened through this supply chain as well. And the middle part, which is a deployment of the ERW, can help remove the embedded emissions between these two, in these two, the supply chains, the mining and the traditional agriculture. So this is the assumption of my model. So the data I'm showing today is only a sample data, and we are using our field trials. We're currently doing a 2-year field trial in southwest part of China in the rice paddy, and I will use that data to correct the model later. And currently, I'm assuming the model calculation based on the 400 hectares of the tropical rice paddy. And based on that, this is the initial result. And you can see the simplified here, the main part, the upper part of the left first column will be the emissions happened as the steps I introduced before when you deploy the technology. There will be transportation, rock application, crushing, and MRV. And what you can notice here is the transportation take a huge amount of the whole emissions occurred. So the 70% emissions, 76% of emissions are coming from the transportation part. And the downside for the green area, that will be the geochemical carbon sequestration happened. That's introduced by the weathering of the silicate rocks in the soil. So adding all up, the emissions emitted and the emissions removed, then we will got the result for the net carbon removal will be 206 tons of carbon per 400 hectares of the paddy field. And this means that 400 hectares of the tropical rice paddy can generate around 206 carbon credits. So that's the data shows. And when you look at the middle column, that is the supply chain I introduced before. It's about the mine tailing industry. If they keep doing in the traditional way to establishing the tailing dam, then it will emit 9 times more of the emissions than the ERW net carbon removal can give us. And similarly to the third column here, in the agricultural industry, that will also introducing 2.4 times more of the additional emissions. So these emissions are all the ERW can bring to us, the embedded benefit. So that's what it looks like. And the next step is we did a techno-economic analysis to analyze the cost for deploying this technology in Southeast Asia. And we did a comparison between the non-Southeast Asian countries and the Southeast Asian countries. And we can see that in Southeast Asian countries, we can save the cost around almost 40%. And they coming mainly from the labor cost and the cheap MRV cost, which is monitoring and verification, the lab sampling, testing stuff, and higher weathering rates. Because in Southeast Asia, we have the higher temperature, higher humidity level, which can cause the weathering happens faster as well, which means the carbon capturing process can happening faster. And this right-hand side is what we mentioned before here in the last slide. You can notice the transportation is the biggest factor introducing the additional emissions to the whole system boundary. So what we wanted is to deliver more effective carbon removals, which means using the same amount of the rock, taking same amount of the land, like hectares of the land, and deliver more carbon credits, which means deliver more carbon removals. So what we need to work on is the transportation part. We need to do an optimization for the transportation. And here is a sample on the right-hand side, is what I did for a case trial for Vietnam. So you can see the red points, red star points are all the quarries available, basalt quarries in Vietnam. And some round dots are the central point of the farmlands in Vietnam. And linking those two together, like using the, you can see my mouse here, you can see some white routes. Those are all available truck routes for transportation. So when I calculated all the possible routes, then I will get a minimum of the transportation routes, which can lower down the emissions emitted from the transportation. Like the truck, they will use fossil fuels. They will use the diesel to run. And how much diesel they use, then will emit more emissions through the transportation. So that's how the transportation is being optimized through this. And the next part will be the life cycle impact analysis. And we are doing this based on the recipe 2016 method. And this is in the current study, this method is recognized as official and all acceptable methods. And what it works is to calculate every different environmental damage, or I would say environmental impact brought by this project or technology. And each step, it will introduce different kinds of midpoint impact. And then that will cluster into the damage pathways. And different pathways are clustered to the endpoint. And we have 3 endpoints, which will be the human health and the ecosystems and resource scarcity. So every endpoints will be quantified in the end to quantify how much environmental impact have been introduced by this technology. And for the timeline, we will analyze it from the short term, mid-term to long term. And you can consider the short term is around 10 to 20 years, but different endpoint that will be different. So different midpoints that will be also different timelines, depending on the standards. And the long term, you can consider it as unlimited, like out of the human lifespan. And here is an initial result for the numbers. I know they are quite not very visually good, so I made some graph for us to visually see it better. So you can see here the fresh water, the ecotoxicity, which implies the potential damage to the terrestrial system. And also for the human cancer toxicity, here is a huge jump. If you cannot locate it, it's around here where my mouse is. So that means this technology can increase the potentials of the damage to human cancer. And we also quantified that these kind of environmental impact on like the downgrading the human health issues. But we've seen like the ERW supply chain LCA results before. ERW is also bringing embedded benefits to mining and farming industries. So the next one will be showing on the without ERW scenario, what will happen, what kind of environmental damage will happen. And you can see similarly here, it's also the ecotoxicity and human cancer jumped from the short term to long term. That means if we don't deploy ERW, that potentially that will be more benefit introduced happens in the future, like in the long term for our future generations, introduced from the tailing industry. And similarly, for the chemical fertilizer production part, it's also happened like a huge jump from the short term to long term. For human health, for ecotoxicity, there will be more damage in the long term. And to gather all the information together from the results, we can see the life cycle impact happens here. Is the red line will be the mining industry, like the traditional tailing dam construction, you can understand it as. That will be short term, mid-term, long term. And that means long term, that will be more damage. So the environmental impact, you can see the zero axis here, and it's decreasing a lot. That means it's introducing more environmental damage, like negative impacts. And the second graph is for the ecosystem. It's showing something similarly. For the resource scarcity, why it's showing like a very horizontal line is because we haven't really used additional resources because we are using wasted rocks. So that's why it's shown like that. And you can see also the yellow line, orange line is a farming industry, like what will the chemical fertilizer production be like from the short term to mid-term to long term. And the green line on the top will be enhanced rock weathering. What will be happen if we deploy ERW? But to notice of that is it looks like aligning with the zero axis, but actually it's above a little bit of the zero axis. It's still introducing, down a bit below the zero axis. It's still introducing some of the negative environmental impact. And the green shaded area will be the total impact, like using the ERW introduced environmental impact to minus the other impacts introduced by mining and farming industry. So we will get the total impact as if we introduce ERW in the real world and how much environmental impact will it bring to us. So definitely the green shaded area will be how much benefit will ERW bring to us. And in the end, in summary, I will get the conclusion as ERW is a promising alternative for traditional mining and agriculture, chemical fertilizer production industry, but ERW cannot provide pure positive impact, but still a promising alternative, valuable to try out. So that's a part one. And the part two is I also started recently with Paul together and collaborating with his PhD student, Hannah Green, on the environmental, like the life cycle analysis in Australia, mainly in the North Queensland, based on the field trial on sugarcane for that part. And we did a comparison between the mill ash deployment and basalt deployment. And here is all the data from Hannah. And the material comparison, you can see like calcium, magnesium, and silicate concentration in the mill ash and basalt. And we can see that these kind of elements are all very effective in the enhanced weathering. And the CO2 rate is also introduced based on this material and based on Hannah's geochemical models. So we use that as an input for this LCA system boundary. So this one, we really want to, as I mentioned before, the transportation is a very important part. So this part of the project, we want to focus on the transportation. And we narrow down the system boundary from the quarry to the farmland. So they ended when spreading the rocks on the farmland. That's because from the previous research, we found out that MRV actually are taking a very small part of the whole LCA emissions. So we did that. And the main steps were including the grounding of the rocks and the transportation from the quarry to the farmland and the spreading on the farmland using the farming vehicles. And these vehicles, the fuel used are all diesels. So, but for the mill ash, because we find out the location of the mill ash, they are mostly very close to the farmlands. So we excluded the grounding part, and it will only including the transportation and the spreading on the farmland. So this is how we did the optimization for our transportation in this project. You can see like on the right-hand side, this is a simplified graph to show the idea that how we do the optimization. Actually, the starting point will be the quarry. You can see quarry 1 and quarry 2. And the centroid will be the central point of the farmlands inside the grid cell. So we divided North Queensland into around 50 to 70 grids. And in every grid cell, we will calculate a central point spatially for the farmland covered. And that will be 2 points linked together. And we will calculate the shortest pathway for all the transportation to happen from the quarry to the farmland. So that's what we did. And in the real Queensland map, we have 53 of the quarries and 513 of the farmlands. And we have that make us like more than 27K of possible transportation routes. And we are filtering from those routes. And here is also we set different scenarios for our optimization. The baseline scenario will be including all those 500 farmlands I mentioned before. So every type of soil are included, no matter how much geochemical benefit they are introducing. And the first optimized scenario will be excluding those soils are too acidic or too high the pH. So we excluded that is because the soil with pH less than 5.9 or pH more than 8, that will introduce positive emissions from the geochemical weathering process. So that is a first optimized scenario. And the second optimized scenario to make things work better, we considered about the transportation part, the whole life cycle of the carbon credit development. So this scenario, we excluded the part of the LCA emissions, which are negative emissions. So we excluded the results from that. We get the ending results of if policy can make things happen in the best way, then we only deploy on the farmlands and only choose the transportation routes which can make the project, the whole process, actually a negative, like net carbon removal thing, not emission happening thing. So, which means in simple words, In the last best optimized scenario, we will have every project actually generating net carbon removal. Not if we deploy on every type of the farmlands, then some of them may generate the carbon emissions, not removals. So that's the main idea. And the result here is the first part, you coming for the different total emissions. For the baseline scenario, as I mentioned before, is we just like brainlessly deploy the rocks on every farmland we can go to. Then that will only be 3.4 about the tons of the million tons of the CO2 emissions in total area of the North Queensland. But if we optimize step by step, you will see like the carbon removals are, the emissions are like reducing more and more. And you can see if you compare the basalt and mill ash, actually the baseline scenario, the basalt is performing better than the mill ash. And in the second optimized scenario, the mill ash transportation rates are also like reduced a lot from the optimization. And here is the net carbon removal rates, which is the carbon removal and minus the total emissions. And for basalts, because it has very strong weathering power, so for the transportation distance, basalt is not that sensitive. So in different scenarios, it's quite stable. And here is a result for the including the grounding and transportation of the cost analysis. So this is a total cost like divided by the net carbon removal amount. So this is a unique cost, like USD per ton of carbon dioxide. And the transportation and the spreading of the rock powders, those costs are mainly controlled by the price of the diesel. As you may be already aware of, the recent war is going on and influencing the global diesel price, the fuel price. So this will also be another character happen politically to influence this kind of deployment of different projects and technologies. And for basalt, grounding will use the electricity from the Australian national grids. And the electricity price will also depending on what kind of energy you are using, whether it will be fossil fuels or renewable energy, or like bioenergy or hydration energy. So that will be all different results. And currently we are calculating based on fossil fuels. So depending on this and comparing to other literatures, they have calculated the biochar, the bioenergy, carbon capture and removal, and DAC, direct air capture, as I mentioned in the beginning. And our technology, like the mill ash, no matter mill ash or basalt, still have a very competitive place for the cost benefit analysis. So here on the right-hand side is the results for the 3 optimization scenarios. And the down 2 part of the graph will be the transportation distance and the relationship with the net carbon removal. So we can clearly see that the negative correlation, when the transportation distance is longer, then the emission is higher, then the net carbon removal rate will be lower. So for mill ash, most of the regions are more than 300 kilometers. Around that, then will be the negative net carbon removal. And which means if the transportation distance are more than 300 kilometers, then we shouldn't do that anymore. Otherwise, it will be introducing more emissions instead of the removals. And basalts are around 440 kilometers, which makes basalt can maybe transport longer than the mill ash. And otherwise, for realistically, we have more like mill ash quarries or like the feedstock points available in the region in North Queensland, but we have less basalt quarries available points for the deployment. And our main findings and applications will be like the On regional scale, the enhanced rock weathering deployments are mainly limited by the transportation and not actually the geochemical reaction rates. And we also provided this kind of spatial optimization LCA framework for those suitable for the agricultural residual and mining residual resources co-located area, such as Australia. And these two different materials can both have the soil fertility improvement potentially, and also comparing to other carbon removal methods, these two technologies are somehow like more promising and competitive. So this is the end of the life cycle analysis. And the last part I will go through very quickly about that is on the stakeholder perspectives. I want to understand like how to make things happen, how to make it actually the deployment scale up in the region. Because as we all know, there's already a technology existing, but still the market is not very ready for that. So in this one, we can see this is a graph for the ERW operations globally in last year, 2025. I believe currently they might already have more deployments already. So you can see the Southeast Asia still remains as an empty space with advanced climate conditions, which can make the weathering happen faster. But to study this, why the things are not happening here and how to make the good things happening faster and better, then I started a pilot interview to understand what would be the enablers and barriers of the deployment of these kind of durable carbon removal technologies for enhanced rock weathering as a case example. So in total, I did 64 exploratory interviews, and the main interviewees coming from Singapore. And they covered from stakeholders in carbon trading industry and farmers, miners, researchers, and policy people, but those policy people are mainly for consultants. And here is some initial thematic analysis result I have got. And mainly the focus will be 5 different things. That will be whether you are aware of the ERW itself, and also for people will speak out of their opinions on the policy landscape of the carbon market development, whether it's ready or not in the region, and whether the credit quality is okay or not, because some of the questioning are surrounding the greenwashing for the different technologies. And also some focusing on the economic feasibility, whether the enhanced rock weathering, for example, they have a high price. Last year, it could be $350 USD dollars per credit, which means per ton carbon removal. You can sell it as 350. And this year, I think in the beginning, January, it reduced to around 300. So what kind of cost can bearing with this price of the carbon credits, and how we make the carbon credit price acceptable? Because as another comparison example, in Singapore, the carbon tax is only 25 Sing dollars currently, and is hopefully rising to 45 in the near term. But it's still, when you compare 25 with 300, that's not possible for people to purchase in carbon credit instead of let the emissions happen and pay the carbon tax. So how to make it more effective? And MRV is also another problem. People are questioning the MRV methodology are not stable enough, not accurate enough, not including like the dissolution of the rock itself. And some rocks might be also washed to the river already, and how you get to filling the gap between the models and field trials. Because what happened in the field sites, they might be quite different from what we modeled at scale. And if you cannot model at scale, that means you will be sampling more. And sampling more means higher cost of the project. So there is a dilemma on how to make things right regarding the MRV standards and to help scale the technology rigorously. And another part in the last point was very interesting, because some of the supply chain stakeholders are involved in the technology, like the miners in the upstream and the farmers in the downstream, and in the middle part, it will be government and the financing agencies. There will be different stakeholders playing different roles. And regarding the carbon credit project developer, they will also like proposing different methodologies regarding the MRV. And some of them are considering combining different technologies. That would be very interesting if you're considering like combine the biochar with enhanced rock weathering together. And some of the researchers are already doing some few trials on that. So that will be interesting to see how to find optimal solution in the end based on different possible carbon removal technologies. So based on these pilot results, I established the current methodology for the later study. I will be focusing on the agriculture-related durable carbon removals to understand better the stakeholders' perspectives on the BECCS, the bioenergy, carbon capture and storage, enhanced rock weathering, and biochar. And through different knowledge inputs from the industry, from the academic literature, and using the mixed approach by doing both the interviews and surveys, I will collect data to combining to do a qualitative and quantitative analysis in the end, and then to provide an outcome to show the different stakeholders' priorities and enablers and barriers for deploy this kind of promising technology in Southeast Asia and Australia. So the ending methodology will be using the natural language processing model, which is a expert that will give me kind of some like the AI power to help me make it faster of my analysis process. And this is a kind of interesting result because I have already shown you this is my manual analysis, and this is the result for the AI results. So it's actually quite similar, but for the AI results, it can make me like analyze the things more quantitatively. So you can see that there's a huge focus for ERW on nature and agriculture, and people are caring about that part of the things regarding ERW. So depending on this point, I think there might be some bias of also myself when doing the pilot interviews. I might be leading more to the agricultural questions because myself is more interested in that as well. So for the future research, official one starts, I will try to avoid this bias, but this is also an useful information to get me thinking one interesting question. For ERW and biochar, both of them have agricultural benefits, but whether it will deliver the financing pathway, which one will be more effective? Will it be like generating carbon credits, or will it be just simply use it as a fertilizer or soil amendments? So which one can actually make the impact from this technology itself, help it scale up faster? Is also one of the interesting questions I want to ask in my following interviews. And I think that will be all of the sharing for today. And I would like to thank all of my collaborators, especially Professor Paul Nelson, for helping me like coordinate and arrange all the things here in Australia, and also to all of my other collaborators to help through in my PhD research projects. And also thanks to the research funding that made it possible for me to travel to here. And also in the down part, maybe you notice the entrepreneurship program. It's also we are trying to explore the commercialization opportunity of the enhanced rock weathering in the region. So if you're interested in that part, I'm also happy to talk more later. And for the left QR code, if you're happy to attend in my interview to speak out as a stakeholder for enhanced rock weathering or biochar, feel free to fill in the form, and we can talk more on that and to generate some valuable input for my interviews. And for the right part is my LinkedIn. Feel free to connect with me if you are interested to talk more. So thank you, everyone. Yeah.
Thanks very much. That covered a huge range of things in a really amazing way, so thank you for that. Has anyone got any questions or comments? I suppose I've got a couple. One around ERW, there are still uncertainties in terms of, it's difficult to measure and how long does it take. So maybe confining my question to comparing biochar with enhanced rock weathering. So with biochar, once you have a ton of biochar, you've captured a ton of carbon dioxide, right? Whereas with enhanced rock weathering, it's a bit more difficult. Have you noticed that difference coming up as an issue with the people you've interviewed, or are you trying to pursue that difference between the two?
Yeah, I think people I interviewed are quite they are all commenting on biochar is a more matured technology, and the enhanced rock weathering, it has a lot of uncertainties because in the long term, when it weathered in the following years, the weathering rates in different soil types are all different. That makes the carbon removal rate, the carbon credits generation are kind of not very accurate. But for the current MRV, the industrial MRV standards, they are trying to set up a buffer zone for the carbon credits generated by enhanced rock weathering to kind of buffer those uncertainties generated in the following years. But some of them are quite also supporting and commenting on that we need more field trials for the enhanced rock weathering, like covering different soil types and different because the farming irrigation system, the farming types, the different crops, as in the rice paddies are quite different from the wheat, the farming techniques, like how much water it will receive. These kind of things are quite complicated, and people are commenting on that. So also I heard some researchers are kind of sensitive to whether the enhanced rock weathering are actually deliver durable carbon removals, because some of the silicate rock powders, they will be left and in the soils as a type of the unstable form and not transporting to the ocean and stored permanently in the end. And when they flow through the river runoffs, that will also weather the bed rocks under the river. So that's also a very uncertainty hard to be accounted. So I guess a lot of problems for scientists to answer, and for some cross-border issues that whether to transport feedstock cross-border between different countries, especially for Southeast Asia. Maybe I have a quarry in Indonesia, but the nearest point for the farmland will be in Malaysia, and how to make that happen regarding the policy-wise of the problems. So that would be regarding the enhanced rock weathering. And for the biochar, I guess it's just things might be simpler, but it also got questioned for the permanence of the carbon storage. So that will be, I will also look forward to hear more opinions on the comparison of these two in my following interviews. And feel free to attend the interviews.
Fiona, did you say? Fiona, would you like to unmute and ask your question?
Yeah, my name's Fiona Ryan at the University of Southern Queensland. A student, PhD student. Can you hear me?
Yes, thanks.
Can you hear what I'm saying?
Yes, we can hear you clearly. Go ahead.
Oh, great, thanks. Yeah, I was wondering, there's some for compliance carbon markets, they usually need some sort of internationally verified system for the MRV. So the usual one is into the IPCC guidelines. I assume from what you're saying that do they have IPCC guidelines for ERW? And then there's the Australian carbon credit units. Do they have, is there a methodology for that? It sounds like you're working your way up towards that. So I'm just wondering how far you've got for these international guidelines and the national ones, the ACCUs.
Yeah, thank you for asking that. I think that's also because the markets are not very ready, because the enhanced rock weathering, as I understand, is only currently the methodology are serving for the voluntary carbon markets, which are published by Isometric and also another carbon registry called Pure Earth. So they provided different MRV standards for the carbon credit developers to align with when developing the projects. And different developers, they will propose their own methodology when they actually doing the project in different locations, such as the developer in Germany and in Australia, in India, they will provide different methodologies of their self, like how they sample, how they monitor, how they calculate the LCA and different things. And for the compliance market, I noticed that last year, there is a proposal for enhanced weathering submitted by Carbon Business Council, but to the UNFCCC, but I haven't followed the latest status of that. So I think, to my current knowledge, the ERW is working in the voluntary carbon market instead of the compliance ones. So yeah, but hopefully in the future when they scaling up and when it's more mature, I think that will be better. Maybe to serve in the international compliance market. Yes.
Thanks for that.
Thank you. If someone hasn't got their mic muted, could they do it? And for the Australian Carbon Credit Unit scheme, there isn't a methodology for enhanced rock weathering yet. Any other questions online or in the room? No? I suppose the other thing I was wondering before I let you off the hook is for the LCA, is there a time assumption for how long it takes? Like, can you build that in, or did you assume it happened within a certain time? Yeah, how does that work?
Yeah, I think currently for my Southeast Asia project, I'm calculating for the first year until the 5th year, because at that time I was doing my case example, the methodology, the industrial methodology requires for MRV for 5 years. But currently things have changed. And for the second part of research in Australia, I think we calculated as the first years upfront of the deployment of the rock powders and the mill ash to the ground, and still the geochemical model will calculate until the 15th year. So we currently show the results only from the first year, but we are able to do a dynamic LCA, which is our ongoing work, to be honest. So thanks for asking. So we are trying to calculate the first year until the following years, maybe depending on the geochemical model input. So that will be a very great resource for us if any of you have potential for good geochemical models for enhanced rock weathering or biochar. So we can do a dynamic LCA to further provide more information for policy implications for the deployment of these different technologies. Yeah, thank you.
Okay. Any other questions? No? All right. Well, thanks. This is a really, really topical area. It's really important, and it's really helpful for us to see the work you're doing, which is, really useful for moving the knowledge forward. So thanks very much for sharing that with us.
Thank you. Thank you for coming, everyone.